Okay. I hope my screen is visible. Okay, let me start. Okay, so given a context-free grammar, we have seen how we can generate a PDA with a single state that accepts by empty stack. And I want to reverse the construction. That is, given a PDA, I want to generate a context-free grammar. So, given a PDA-M, I will actually generate a PDA-N, and then I will reverse the construction to generate the grammar. Okay. So M, I make some assumptions, accepts by both final state and empty stack, and I assume that T is the only final state. In fact, we have made a construction where we can convert any PDA to a PDA of this form, which accepts by final state and empty stack, and there is only one final state. N, on the other hand, has only one state. And therefore, there is no question of, I would say, acceptance by final state. So this accepts by empty stack. Okay. So this conversion from M to N is very tricky. N to G is just the reverse of the CFG to PDA construction. So let us not worry too much about that step. So this step I need to explain, and this is where we stopped in the last week. Okay, so the construction M to N. M may have multiple states. N will manage with only one state. So as I mentioned in the last class, N, in a sense, stores the, I would say, state of N, M, and its stack, along with other symbols. Of M. So question is how we can achieve this. I will give you a formal construction soon, but before doing that, let me give you an example. This is a simple example, but this has a relevance in the context of our construction. Let us say this state is S, and there is a final state, let's say T. read A. And I have an epsilon transition here. A is there, keep it. Bottom marker is there, keep it. And here I have so what is the language accepted by this machine?
A power n, B power n.
Yes, A power n, B power n. So this accepts A power n, B power n. We have seen this machine earlier. For all n greater than or equal to 0. Okay. So what I will do, I will build a machine that for the moment will store a state of this machine and the symbol A or this. Okay. So its start symbol is S and this, indicating that this machine starts in state S and its bottom marker is this. Okay. Note that in the start state S, this machine can never pop anything. All the pop things happen in the state T. Okay. Therefore, I should have some transitions like this. Okay. So one by one, let me convert A and you read S. Then what happens? I am going to push some A's. Okay. And I am still in the push mode. But then this is no longer exposed. It will eventually be popped when I am in state T. Agree? The moment I am pushing something, this thing goes down and I can pop it only in state T, not in state S. But here I have S to indicate that I am still in state S. Not I mean this guy. This guy is still in state S. Okay, so now if I look at the second one, M is in state S, and this is at the top of the stack. I will continue to stay in that state, but the previous A that I have that triggered this action will have the state changed to T. Again, the reason is clear. This A cannot be popped in state S. Okay, and therefore I have to do something like this, but I am pushing this in order to indicate that I am still in, or this machine M is still in the push mode. Okay, so this is how I refresh this and this. Then I have to handle this. Okay. First one says that S, comma A will be on the top of the stack. Now I am going to state T. So I will change that thing to TA. And second epsilon transition, this thing happens if no A's are read. If no A's are read, I am in this situation. S, comma this. Replace that by T, comma this. Okay. Now I have to keep on popping. If I see T here, pop. If I see, so I made a mistake here. It should be an epsilon transition. Yeah, just pop this thing at the end, epsilon. If I see T, this, pop it. Okay.
Sir, the above PDA, does it accept by empty stack or final state?
Both. Look, empty stack because it will have to eventually get rid of this. Right. So that means in order that this is exposed, the number of A's and number of B's, each A pushes an A, each B pops the corresponding A. But if and only if this is perfectly matched, okay, this is exposed, then it will clear its stack, empty its stack, and accept. On the other hand, this converted machine can accept only by empty stack. There is only one state. Agree? How this example works? I'm just remembering whether the original machine is in the push mode or in the pop mode by storing this S alongside the regular stack symbol for this machine, M. So this is my M. This is my N. Okay, so this example is actually, I would say, a little bit misleading because this is a very simple machine. So there is always a transition from S to T, but no transition from T to S. S is meant only for pushing, T is only for popping. But in reality, more complex machines may have multiple states where we can do both push and pop, and it may come back, okay, from S to T and then again T to S, or from S to P to Q to T, and then again back to S. This kind of general behavior is possible. And although this is a very simple thing, just by remembering one state is not going to do the work. I cannot prove it. Okay. So that requires some formalism.
Sir, I have still a doubt in the first machine.
Tell.
Sir, here, if we read the entire stream and we are in a final state, then that string should be accepted.
What is the question? No, I didn't understand.
So for example, if I read just a power n, and then I make an epsilon transition to t,
Correct.
and t is a final state.
T is a final state, but the stack.
So, but it does not care what is in the stack. If it is in a final state and...
Oh, that's why I mentioned Emacs saved by both final state and empty stack.
Okay, sir.
Okay, it's not just empty stack or just final state, both. Okay. Okay, so any other question?
Yes, sir. Sir, in the first transition of A S comma bottom marker, I am unable to get this T comma bottom marker, sir.
Look, this is the pop state, right?
Yes, sir.
Okay. So I can pop this out only if I am in state T. In state S, so note that this stores the information of both the state and the stack top.
Yes, sir.
This symbol means that the original machine M is still in the push mode. At that point, popping this out is not allowed.
Yes, sir.
Okay. But then an A has come. Okay. So I will have to push this A and still stay in this mode until I do this epsilon transition. Okay. So this is A, this is why this is S. But now this is no longer exposed. It will once again be exposed in state T. That is the reason I am replacing that S comma bottom marker by T comma bottom marker.
Okay, okay. Yes, sir. Yes, sir. It's the change of S to T. Okay, sir. Got it.
You see that this can be popped out or this can be popped out when A can be popped out or this can be popped out when only when the original machine is in state T. Okay.
Yes, sir.
Okay, good. Any other question? If not, I go to the generic construction. It's slightly, I would say, complicated. But we will see that this construction will essentially give the same PTA if I run on this. Okay, essentially means, okay, whatever, I will see. Okay, so what I will do is not exactly storing only this S and T or some single state. Let us think of this situation. This is the working of M. Let's say it sees something like A on the top of the stack, and there is something below it. Okay. Suppose that at this point it is in state P. Now note that M accepts by empty stack. Therefore, if it is going to, if the input is in the language of this machine, there will definitely come a time after consuming something from the input when A will go out of the stack. It will have to happen if the machine M accepts the input. At some point of time, A will have to go out of the stack. In other words, so there must be a time after reading some X when only, okay, and also note that until this part A or whatever is pushed further in future, until those things are popped out, this part which I have shaded cannot be touched because it's a stack. Okay, and maybe at that point of time it is in state Q. Okay. So what I will do, instead of pairs, I will use this as my stack symbol. So this is basically a member of Q cross gamma cross Q. Now this is for M, this is for N. So what N will do during the simulation process, this has only one state. Okay. And it has something here, here, here. But the working of N will be something like this. If it has this symbol P, A, Q, okay. It reads the same string X and can eventually get rid of that extra symbol on the top of the stack without touching whatever is below. This is how N will simulate the work of M. It's not just remembering one state, but this formal way. Okay, it's little difficult for you to visualize, but I will give you soon an example. Okay, so starting from P, it reaches Q after reading X. So it's something like this. What is the current configuration of M? P maybe I write X followed by some alpha, and I have A, gamma. Gamma is this part, X is whatever is remaining. This is the configuration at this moment. This will eventually go to the configuration Q, X is consumed, and just this is consumed. This is for AM. And here what will happen? P, A, Q. This is on the top of the stack. The state is always start, so this is not important thing. Followed by something, okay, the same, okay, X alpha. No, sorry. Should write this thing first. X alpha should be first. State is star. Then in one or more steps, this machine N, this is followed by some string gamma, not the same gamma, maybe delta I like, right? It will have the effect, it will stay in state star, it will read alpha, it will read X, and it will get rid of this. So the idea is that the simulation of N, simulation of M by N, is based upon the construction motivation that this thing happens if and only if this thing happens. Okay. So then, what should be the initial stack symbol or initial stack symbol or bottom marker? Basically bottom marker, initial bottom marker for N. M accepts if and only if starting from S, it can go to the single or unique final state T. Okay, with the stack empty. So how I should prepare star to handle N to begin with? This will be machine M will start from S with this thing on the top of the stack. It should eventually reach T with this thing removed. Happy or not?
Yes.
Okay, so M accepts if and only if it can go from S to T with empty stack. And by this equivalence, this machine accepts if and only if it can get rid of this symbol from the top of the stack. Okay. So this is how I initialize N. Okay, so this is N. So what will be the transitions of M? N. So let us say that P A Q B1 B2 Bk is then the transition of M. Okay, so what does it mean? For some K, K may be 0, K may be 1, K may be 2, K may be 10, something like that, a constant. Okay. So this means that something is sitting there I am not worried about. Machine M is in state A, it's reading A from the top of the stack, from the input. A may be epsilon also, it may be an epsilon transition. And keeps these parts exactly the same. Replace this by K symbols, B1, B2, Bk. Of course, if K is 0, this is immediately popped out. Okay. If not, and this will go to state Q. Okay, so let us call this Q0 for a reason that will be clear soon. Okay, so let's assume that K is greater than or equal to 1. So this new stack top is replaced by K new symbols. And I am interested about the behavior of M where this A can be taken out. Okay, eventually keeping this part exactly constant. So that means one by one, it will have to get rid of B1, it will have to get rid of B2, B3 up to Bk. Okay. So this means after reading some string x1, this machine can get rid of this B2, B1. This is still unchanged. Maybe at that point, the machine is in state Q2. And then there must be a situation after reading some string x2 from the input, it will get rid of B2. So only B3 to Bk will stay. And this part remains unchanged. This thing goes on. Eventually, so this, let's say this state is Q2. Eventually, after reading something like xk, this machine will come to state Qk after getting rid of this Bk. So, if the original machine M can get rid of this A, Okay. And if it has a transition of this, and if this is applicable for getting rid of A, then this must be the situation. A is replaced by B1 through Bk. There must come a time when B1 is got rid of. And again, there must come a time when B2 is got rid of, and so on. So eventually all of this B1, B2, Bk are one by one popped from the stack, leaving the whatever below each of the symbols unaffected. This is bound to happen. Yes or no?
Yes, sir.
Okay, so the simulation step will be what? Okay. This is triggered by reading A. So I will do this thing. I will convert this transition to this form. A single state. Read A. This is B. A. Eventually in state QK, it will get rid of this A. So P, A, Q, K. Replace this by from Q0 to Q1, consume this. But you have to introduce K new symbols. Q0, B1, Q1. Right. Go to Q0, consume B1, end up in Q1, Q1, consume B2 from the stack, go to state Q2, so on. Eventually you are in state QK minus 1, get rid of BK and end up in state QK. This is how I convert this transition for M to a transition which is a loop for N. The only question that remains to be answered is that how do N or how does N know beforehand what is Q1, Q2 up to Qk? Q0 it is getting from this transition table. But what is Q1, Q2, Qk? Okay. So the idea is that N guesses Q1, Q2, Qk. For all possibilities of this Q1, Q2, Qk, it will add this transition. If anything works, it's fine. If nothing works, then definitely this original machine can also cannot also get rid of this A. Okay. So that's actually the end of the construction. It's slightly more complicated than this example. But if I apply this construction on this machine, we will see that we will eventually come up with the same thing, this one. Okay, So let us see. Happy or not? It's slightly complicated, I understand. But this is how the simulation of M by N works. Okay. So I think I have this picture again. Yes. So we have these things. S, A, if this is read, A is pushed. So this is basically the same machine as this. This. Okay. And this is my N. Okay. There is a single state. And if I apply the construction, let's say on this. So there are two stack symbols, A and this. So it is S to S. So Q0 is S. So it will guess something like what it is after getting rid of this A and after getting rid of this bottom marker. So S A, for the moment let me write Q2. Okay. Sorry. What is there at the top of the stack? Want to get rid of this A. The AA. So this guy. A it will consume from input. This one. This will be replaced by S, because this is S. A will be got rid of in some state Q1. S, eventually this will be got rid of in state Q2. Now, of course, there are four possibilities. Q1 can be S or T. Q2 can be S or T. So for this, if I follow the mechanical construction, I will generate four transitions, one for each of the gases of Q1 and Q2. So for example, I may have this S, SAS, S, this S for the gas Q1 equal to S, Q2 equal to S. Okay. So I will generate four transitions out of this if I follow the mechanical construction. Okay. Now, because this is a specific example, I can do some kind of manual tuning, the human manual tuning. Okay. If I have a situation like this, I am in some state, S, some symbol, the top of the stack. Let us give it some name. U may be A or the bottom marker. This may be S or T. Okay. Then you see that. Okay, so this may be P. So P is in S or T. U is in gamma, that is this or this. Then you see that the machine will end up in S, starting from whatever state. It will end up in S And in the process, it has got rid of this symbol on the top of the stack. Is it possible?
No, sir.
Okay, because if it ends up in state S, that means it will always stay in state S because it cannot come back to S from some other state. In this example, of course. Okay. And okay. So that means that these symbols are useless. Of course, this is only for this example because I have a very specific PDA. Okay, so these symbols are useless because nothing can be popped in state S. Okay, and there is no way of entering state S other than being there itself. Okay. Therefore, it turns out that these are the only 4 useful stack symbols. These are useless, so these are the only useful stack symbols. But note that this T is constant here. T, it has to be T, because otherwise there is no question of getting rid of these or this in state S. It has to be T. Okay. Therefore, if I rename this as S comma this as S comma A, this as T comma this as T comma A, and slightly rewrite these things, do it, you will see that this will exactly be this. So remember A, S bottom marker, SA, T bottom marker. Okay. So S bottom marker, A consumed, S comma A, T comma bottom marker. Okay, actually this gives 4 guesses, but this is the only useful thing. The remaining things we can manually throw out. Okay, because we can see this picture and we can do some kind of work on it. Also look at this epsilon T comma this, pop it out. And if I look at that thing, epsilon T comma this, pop it out. Okay. So it is precisely this machine that follows after doing some throwing away of useless transactions. You agree?
Yes, sir.
Okay. So that's basically this construction. Anyway, it sounds a little bit complicated, but this is a way of doing it. And that actually establishes that given any PDA, I can convert it to a PDA of this form, and then I can reverse the construction to generate a grammar out of this. Okay, star is not important. It's basically you replace this. This is a non-terminal symbol. Replace this by A followed by this. Replace this A followed by this, and so on. Okay. Okay, so that leaves us with just one more, I would say, subtopic. So maybe I just start it. Tomorrow I will finish it within half an hour. And yeah, so let me know if this part is clear.
Sir, the simplifications we made by just observing that P.
Yeah, this is just a manual thing.
Yes, sir. So the construction would be lengthy, but still correct if we hadn't.
Otherwise, it will be correct. Only thing is that these other transitions that you introduce, these are useless.
Okay, sir. Yes.
You cannot get rid of U if you end up in state S.
Okay, sir.
Okay. So, any other question? Okay. Fine. So then what I will do, I will consider a class of PDA which are called deterministic PDA. Okay. But unlike deterministic finite automata, we need to have formalities because there is a stack. Okay. So if the machine is in state P, A on the top of the stack, then there are two possibilities. There is a unique transition to handle this situation. That is deterministic, right? There is a second possibility that there is no such transition, but in that case, there must be a transition of the form P to something. So if you can consume A, do it. When you are in state P and seeing capital A on the top of the stack, do it. And if there are no such transitions, there must be a way out using an epsilon transition. So this is epsilon transitions are allowed in deterministic PDA, but this has to be taken in this light. So this is the determinism part of it, deterministic part of it. Okay. Second assumption. Okay, maybe I write it this way. A DPDA never halts. Okay. Even after it has read the entire input and it is supposed to be in a so-called final state. Okay. And it will continue to stay there. It's a kind of dummy loop. Okay. It never halts. And if it does not accept, then also it does not halt. Okay. So a DPDA never halts or gets stuck. Okay. This essentially indicates that this bottom marker is never popped out. Because if the stack becomes empty, the machine gets stuck. No transition can handle an empty stack. Therefore, we will make the assumption that this bottom marker is never popped out, so that the machine never gets stuck even after accepting. If it is in some accepting configuration, it will stay there forever. This also implies that since this can never get out of this stack, DPDA can accept only by final state, because it cannot get rid of, cannot empty its stack. And then I make another assumption. The input is terminated by a special marker, special symbol, and let us give it a name, something like this. Okay, note that a non-deterministic PDA can assume I would say guess end of input and make some action based upon that, like switching to final state or something like that. But a DPDA does not have this luxury. It cannot guess. Okay. All what it does is by making deterministic transitions. And so we append the input string by the special symbol not in the input alphabet to indicate that end of the string is reached. Now you can take your decision and stay there. Okay. So it accepts if and only if starts this, well, input first. X this. Okay. Goes to a final state. Sorry, this is not X. Okay, anyway, I should stop now. Anyway, just give me a minute. This is there, and also this is there on the input tab. This entire thing is consumed. Something is there in this stack, but this is never popped out. F is a final state. So language of M is this for some. Okay, so this is the set of all X such that this happens for some final state F. Okay. Okay, so we will look at an example of a DPDA tomorrow and some properties. So maybe I will take half an hour or so. And so these are the things. For every situation, there is a unique way of doing or evolving. Never halts or gets stuck, and therefore this cannot be popped up. So that means it can accept only by final state. And the input is terminated or appended by the special symbol, not in the input alphabet, to indicate that the end of input is reached. So you can now deterministically do something, take a decision, something like that. Okay, so we will continue tomorrow. And then SK will take over with Turing machines. Okay, so let us stop now.
Thank you, sir.
Thank you, sir.
Okay, see you tomorrow.